and nothing. I have to change the plan. So don't worry. I will give you several days to complete the final exam. We will meet as usual next week. Maybe we have a short lecture before I release the exam file, and then I give you several days, and please submit me by the deadline. Okay, that will be specified later. Okay. So far we consider two types of tests. Okay, right tail test and lower tail test. It will be interesting to look at two tail test later. Okay, so this is the one example of the two-tailed test. Okay, so in this example, a medical rehabilitation education foundation reports that the average cost of rehabilitation for stroke victim is 24.70. Okay, not point, but 24,652. To see if the average cost of the rehabilitation is different at a particular hospital, a researcher selects a sample, a random sample of 35 stroke victims at the hospital and find that the average cost of their rehabilitation cost is 26,343. And the standard deviation for the population is this one, and at this level we can conclude that the average cost of the stroke rehabilitation at a particular hospital is different from this value. Okay, so we want to know if the cost of the average cost of stroke rehabilitation at a certain hospital is different from this value. This is a specific value. We want to test that the average cost of stroke rehabilitation at this certain hospital, whether they are different from this. So in this case, you can state the hypothesis and identify the claim. So this is the initial value, right? And you want to test whether they are different or not, right? So then in this case, different can be greater or less than. That's why you come up with the different. It is in this case a two-tailed test, right? This is your claim, and based on the sample from the certified stroke victims, it support our claim or not, right? Okay, so we want it to be 0.01 significant level. So with this significant level, we have to find the critical value, and then we end up with these two values. Why? Because it is two-tailed test. So later on, we have to compute the test value. Okay. So in the sample mean is given, sample mean here. Okay, based on these 35 victims, we found that on average they spend this amount. That's why this is the sample mean. And then the population standard deviation is this one. I mean the sigma. And the initial claim is this. Then you end up with a test value of 3.04. 3.04 is between these two values. So just like it inside the non-critical region, right? Because for the two-tailed test, there are two parts of the rejection region. The value which is less than this one or greater than this one. I'm sorry, it's greater than this in the rejection region. So this value fall in the rejection region, so you have to reject the null hypothesis, right? Yes. Here, this is a rejection region. We have two parts: the value less than this value and the value greater than this. And we found our test value to be 3.04, which is inside this part of the rejection region. That's why when our test value is inside the rejection region, we have to reject. Okay. So how to reject? Okay. Summarize, there is enough evidence to support the claim. You reject this null hypothesis, it means that you support H0, which is the claim, right? The claim. The claim is the alternative hypothesis. And once you reject it, it means you support the claim, right? Okay, so there's enough evidence to support the claim that every cause of rehabilitation at a particular hospital is different from its value. I mean that we support this. Again, this support just from the sample you collected, right? But it may not true that the claim is correct, right? Because there some error may happen. Right? Okay, here. Here is the code, right? Here is the code for the first example. Okay, the code for the first example, which is this one, right? This one. I just summarize all the amount related to this one, and then I can come up with this R code, right? So you have to specify the alpha to be 0.10, and the initial value of the population mean is this value, and from the sample you come up with the sample mean to be this, and the standard population standard deviation is known, okay, to be this, and you choose a sample of size 36, and then this is the formula for the critical value. Okay, I'm sorry, not critical. The test value, and then this is the critical value C alpha, right? C alpha. You can get C alpha from this. Okay, I already explained you. Okay, already here. So this is how to decide on your conclusion. This depends on the Z value you computed from the sample, right? So you may look at this conditional in R programming. Yes. Instead that if Z value is less than the critical value, this means that Z is inside the rejection region, right? Because this is the left tail test. I remember from the first example. So if Z is in the less than the critical values, it means that it falls inside the rejection region, then your conclusion is to reject the null hypothesis. Reject null. Else mean if Z is greater than Z alpha. Else print there's not enough evidence to reject the null hypothesis. This is the code for the left tail test, right? So I already have it here. Okay, here I have it here. Okay, okay. This is alpha x bar, and I just list down everything, and this is the conditional code that. Okay, so once everything is input, so I have to run this code. Okay, I just select all and then control enter, and then I will come up with this result. The result is not to reject the null hypothesis, right? The result is not to reject the null hypothesis. And we also found this same thing. There's not enough evidence to support the claim. Oh, no, not this example. Oh. Okay, I guess this is okay, this is a second example, 7, right? We end up with there is not enough evidence to support the claim. It means that we have to do not reject H0, right? Do not reject. And by R, we found that we do not reject the null hypothesis. Just come up with the same result. So this is how you do it hand by hand, right? Manually. But once you want to use the R, just run this code, and it's just a piece of cake. Just enter the numerical value and then just give it. So it seems that calculation doesn't matter, because now you have a very wonderful statistical software to assist you in numerical calculation. But the thing is that you have to know how to interpret the result, right? Okay, you know how to interpret the result. Okay, that is the main thing. Originally, when the computer science is not that good, people just use hand and come up with a very complicated calculation. But now we have very good computer software that can assist us on that matter. But still, we have to know how to interpret the result generated by the computer. Okay, you may ask, okay, it sounds that we have to write very complicated code. Okay, because R is free, and then the code can be write by using a series of commands, different from the SPSS that you have to put only the number and then we generate you very nice result. But as I said, it's not free, right? SPSS, and sometimes it's not flexible. In R, you can write any code to reflect the real situation you want. And even here in Excel, actually Excel, there's no hypothesis testing for a single sample, right? Just like our example. You have to download the add-in name Megastat, which is not free in this case. So in order to use Excel, you have to install this add-ins named Megastat. And I searched that it's not free, so you have to pay to come up with this value. But usually it gives a different the code, the software just give you a different calculation, which will be considered later. Okay, so I think we should stop for a while to take a break. For 10 minutes, because have to drink some waters. So any question before breaking, before the break? Usually Lakana have a question, but today's you sound silent. Should have one. Okay, you don't have. Okay, so just for 10 minutes, we will resume at 4:36. Okay, 4:36 to finish the remaining section. Okay, I'm trying to finish by this week because we will have final exam next week from next week. Okay, so just disappear for 10 minutes. Okay, hello, welcome back. You still here? Okay, thank you, Sing Mei. We still have 5 people in this class. Okay, so let's continue. Okay, this is the last part that we deal from the first section. Okay, so so far you see that once you carry out a hypothesis testing, you have to decide on the significant label, right? The alpha. So it could be 0.05, 0.01, or sometimes just 0.1. So this is nothing but the seriousness of the type 1 error, right? Because the significant label alpha is nothing but the probability of the type 1 error code. So it depends on you how you serious with the type 1 errors. If you choose alpha to be very small, 0.01, it means that you want the type 1 error to be occur at only 1% of the chance, right? And so far, when you decide on the the significant level, you have to compute the critical value, right? And you have to base on the critical value to decide whether to reject the null hypothesis. But in some statistical software, it will not give you the critical value, but instead it gives you the p-value. Okay, it's another value that help you to decide whether the null hypothesis should be rejected. Originally, we see that we based on the critical value, and now we are based on the p-value. So what is p-value in this case? Okay, p-value is the probability value. Okay, it's the probability value, and what kind of probability it is? It is the probability of getting the sample statistic. Okay, in the direction of the alternative hypothesis HA or H1 when the null hypothesis H0 is true. Basically, if you look at this example, if you look at this example, this is the, in this case, your significant level is 0.05, and you found that the critical value is 1.65. It means the point that correspond to the area to the right under the curve is 0.05, right? And your test value in this example is 3.39. So the p-test, okay, the one I just mentioned a while ago, the p-test is nothing but this area. Okay, the area under the curve to the right of this test value. This is mean the p-test. So instead of comparing the test value with the critical value, you will compare the p-value, which is this area. You have to compare this to the significant label, the alpha. So again, if you look at the critical value and the test value, you will see that the test value is fall inside the rejection region, or in other words, it is greater than the critical value. So you have to reject the null hypothesis. But in the same case, you may just look at the area. Okay. This area corresponds to this test value is smaller than the critical, the significant label. So you also reject the null hypothesis. So nothing, p-value is the area under the curve correspond to the test value. So if you look at the definition by word, maybe it's a little bit complicated to understand. But as I said, this is how we define p, right? P-value. P-value is the probability that okay. A while ago we look at the right-tail test. Okay? The right-tail test. The p-value is the probability that the test value, okay, greater, the test statistic greater than the test value. Right? I mean the area correspond to the test value. Okay, by knowing that the null hypothesis is true. Okay, for the left-tail test, we define in a corresponding way. Okay, for the left-tail test, your p-test in this case is this area, right? This area. And for the two-tailed test, you have to define p in a different way. You have to count the area under the curve at the test value, and the area under the curve at the negative of the test value. I mean, here our test value is 3.04, so its negative is negative 3.04. So the p-value in this case is this small area at another small area here, right, which correspond to the sign of the test value. That's why you see the definition is one, the test is two-tailed. We will see that it involves the absolute value, right? That is how it means by it. Here, TS refer to the test statistic. So far, our test statistic is the Z, right? The Z test, the Z distribution. So how to decide based on the p-value? Okay, as I said, you have to reject the x0 if p-value is less than the significant label. Right? Otherwise, you have you do not reject the X0. Just like I explained a while ago, this is how you can reject or not reject the X0, depend on the p-value. Why we need p-value? Because the code I give you a while ago doesn't involve with p-value, but only the critical value. You have to compare the the test value with the critical value to decide whether to reject or do not reject the null hypothesis. We need p-value because mostly in statistical software, it will print out the p-value. Okay. So for example, here we run by Excel. Okay. As I said, the Excel, Microsoft Excel do not provide you the statistical tool for hypothesis testing of a single sample. You have to install this add-ins called MegaStat, so that you can use Microsoft Excel to do the hypothesis testing. So this is one example that when you enter the data and you will receive this numerical solution from the MegaStat. And one, as you can see in the last value, you see that this is the p-value, right, which is 0.3495, and it carry out for the one tail test, or the left tail test, because lower mean left, right? Okay, and you don't find the critical value here, right? Cannot find the critical value, so you see only the p-value. So if you want the significant level to be 0.1, so this is greater than, in this case, p-value is greater than the significant level. So you have to do not reject the null hypothesis, because based on the this, if the p-value is less than the significant level, you reject, but a while ago p-value is greater than, right? That's why we do not reject X0. So maybe it looks simpler to based on the p-value rather than the critical value, right? So it depends. You may decide on the critical value, significant level alpha, and then you have to compare it with the p-value generated by the software. Okay, by the software. Okay, this is the rule again. Okay, how to decide whether to reject the null hypothesis based on the p-value. Okay, here for the upper tail test, I refer to the right tail test. When you compute the test value, okay, this is the p-value, right, correspond to the right tail test, the area and the curve to the right of the test value. And for the lower tail test or the left tail test, the p-value is the area under the curve to the left of the computed z, right, or test value. And for the two-tailed test, you have to combine this area, right, together. So in other words, it's given by this formula. This phi is the CDA function for the standard normal distribution. So it just summarizes this situation. Okay, so let's have a look at one example on how to use the p-value to decide on hypothesis testing. So in this example, a researcher wishes to test a claim that the average cost of tuition fee and fee, okay, it should be tuition fee at a 4-year public college is greater than this value. She selects a random sample of 36 4-year public college and finds that the mean to be this. Okay, actually this is the sample mean, okay, because it calculated based on this sample, right? And we know the population standard deviation is this. And the question is that is there evidence to support the claim at this significant level? And we require to use the p-value method. So to summarize, first of all, as the previous one, you have to state the hypothesis and identify the claim. So the initial value is this, right? And this is our claim. The researcher claimed that the average tuition fee, okay, the average tuition fee of at a 4-year public college is greater than this value. It is the claim of the researcher. And then you have to compute the test value. Again, we use this formula for the test statistic, because our sample size is large, right? 36, so we don't need normality assumption. And then you, based on the value given, you found that the test value is 2.28. 2.228. You have to compute the p-value correspond to this, right? P-value. So the p-value in this case is, you found z here, right? 2.28, and you want this area, okay? That will be the p-value. So how to do that with R? So to get the value with R, you have to, I say, okay, I hope you can see this clearly. Z is 2.28, right? And we want the p-value. I denote it by p, okay, value. It equal to the p-norm. Okay, maybe d-norm. Okay, d-norm of z, right? D-norm of z. And by default, the lower dot tail, okay, lower dot tail is okay, lower dot tail equal to false. By default, false. So, okay, let's try to run this. Oh, lower dot. The denom p okay, we have to specify the mean. Okay, the mean equal to 0 and standard deviation equal to 1. Okay, I'm sorry, we forget to specify the mean and the standard deviation. Okay, and then so in this case, p value is this. Okay, we found it to be 0.011. Okay, 0.011. Okay, here, which is this case, right? 0.011. By using the table, first of all, you have to find the area to the left of this z, right? But the p-value is the area to the right. Okay, to the right. So you have to subtract the area to the left from 1, right? And then you obtain the area to the right, which is 0.011, which is given, okay, by R with this code. Right? Okay, so I don't recommend using the table, but using R, right? So now you found that the p-value is 0.011, and then your significant level you choose beforehand to be 0.05. So in this case, your p-value is less than the significant level. When it's less than, you have to reject the null hypothesis, because based on the decision rule, when the p-value is less than the significant level, you have to reject H0, right? H0. So this is your decision, you have to reject it. Okay, here, okay, here, yeah. This is the your significant level 0.05, and this is the t-test, the test value, and the corresponding p-value is 0.0113, the area under the curve to the right of this test value. Okay, so how to summarize the result? Okay, there is enough, you can say that there is enough evidence to support the claim that the tuition fee at a 4-year public college is greater than this value. So you reject H0, mean that you support the alternative hypothesis H1, right? So it means the claim is supported by the data we collected, right? But again, it's not mean that your claim is true. It's just supported by the data, by the sample you collected. But make sure, please take note that if you change the p-value, okay, if you change the p-value, I'm sorry, if you change the significant level, the p-value is still the same, right? 0.013, because the formula to come up with z or the p-value is just solely related to the test value, and as you can see in the formula, it's not involved with the significant level alpha, right? Significant level just change the critical value, but it doesn't change the test value. So with this test value, we always have this p-value. So once you change the significant level to 0.01, in this case the p-value is greater than the significant level. So you come up with a different decision, right? Because now the p-value is greater than the significant level of 0.01, you have to not reject the null hypothesis. Okay. As we note here, okay, if the researcher chosen alpha to be 0.01, the null hypothesis would not be rejected, right? Since the p-value is greater than the significant level. So it depends on how you choose the significant level. Sometimes with a certain significant level, you end up with rejecting the null hypothesis. But once you decrease the significant level, you may end up with not rejecting the null hypothesis. That's why this is how we have some guideline for p-value. Okay, so if you compare the p-value with the significant level, okay, if you found that the p-value is less than 0.01, okay, reject the null hypothesis, and in this case the difference is highly significant, right? Because the p-value is very small. Okay, it's because the lowest significant level statistician always use is 0.01, right? And now we found that the p-value is less than this value, so in this case the difference is highly significant. But if the p-value is greater than this but lower than 0.05, in this case reject the null hypothesis, but the difference is significant, not highly significant. You still reject, but the way of your rejection is significant. If the p-value is greater than 0.05 but greater than less than 0.01, consider the consequence of type 1 error before rejecting the null hypothesis, right? Because in this case the error of the probability of error 1 is 10%, right? It's 10%. So you may reject or not, is up to you. But if you reject it, just consider the consequence of the type 1 error, because you may reject it while it is true, right? While it is true. And the probability that it is true is very high, 10%, right? 10%. And if a p-value is greater than 0.10, okay, do not reject it. Do not reject the null hypothesis. And in this case, the difference is not significant. Not significant. So what is the difference here? Okay. The difference of the real value to the initial value, right? We mean that, right? The real value to the initial claim, right? This is u0 and not significant. The difference not significant mean you do not reject it, right? Do not reject the null hypothesis, mean that the real mean is can be something like this, right? Equal to the initial one. Not significant difference. Okay, this is the code. Okay, for the R code for when we consider p-value instead of the critical value, right? So I give this example because this example you end up with rejecting the null hypothesis, right? So I want to test with R whether it's generate the same result. Okay, so I name this file which is C test with critical value. I already sent you, right? I already sent you. So in this case, just run this. Okay, control all and then run it, and then okay, there is not enough evidence to reject the null hypothesis, which is the same as the result here, right? Okay, I don't know which example is this, but the code is for the p-value. Okay, this is example. You can try this by yourself because we have several examples here in the slide. I will send you again the slide because a while ago I noticed some